Hi, thanks for checking out my video. This is section 4.6, stretches and shrinks in the absolute value family. This goes along with the top handout from the packet for 4.6 through 4.8. This is our first type of transformation where we have the object actually changing size. With the yellow car that you see here, I found some nice lame clip art for this lesson. And this would be an example with the yellow car of a reflection. It's the exact same size, but it's flipped the other way. That was called a reflection. With the tree, if we slide it to the left, or slide it to the right or up or down, that was known as a translation. The objects did not change size at all, they only changed their position. This would be an example of what's known as a rigid transformation. Rigid transformation, they change their position but not the size. Going back to that first page, now we have our first transformation. This is known as a dilation, where this dinosaur will get smaller or larger, So with the transformation known as a dilation, we finally are changing the size. And the way that we're going to explore dilations is through what's called the absolute value parent function. So it says here on your note handout to graph the parent function below, y equals the absolute value of x, and label it with key points. So let's take a look at the absolute value function by graphing it on our calculator. If you take out your TI and you go to y equals, you can graph the absolute value function by going to math, and then over to number, and then option number 1 is the absolute value. On some of the newer calculators, it'll actually put those bars in place, but my version is a little bit older and it says ABS for the absolute value. Regardless of whether it makes the bars or not, when you hit graph on a standard window, it should produce this V. So it looks a lot like a line that sort of bounces off the origin and goes up the other way. And that's actually exactly what it is. So if we take a look here on this screen, of the absolute value function, it basically goes like this. If we made a table of values x and y, when you plug in 0 for x, the absolute value of 0 is 0 for y. So there's a point in the middle at 0, 0. Again, we're graphing the absolute value of x. What this function does is it basically takes any negative number and makes it positive, and it keeps any positive number positive. So the absolute value of 1 is 1. The absolute value of 2 is 2. So it would proceed in this fashion up and to the right. If you put negative numbers in, however, it turns them positive. So negative 1, 1, negative 2, 2, and so on. So the absolute value function is going to look like this. We call it a V-graph. So that is the basic parent function. I want you to draw that on your paper and then come back. All right, now we have the examples A, B, and C of the functions y equals 2 times the absolute value of x, y equals the absolute value of x over 3, and then a mixture of the two of them, 2 times x over 3 with the x over 3 in the absolute value bars. So I gave out some red graph paper that I'd like you to use, and I'd like you to put each of these on a separate grid. I'm going to do them all on the grid that you see right here. For all of them, let's go ahead and graph the parent function, y equals the absolute value of x. So that's a V that starts at the origin, and up and to the right, it goes over 1, up 1, over 1, up 1, over 1, up 1. As you go to the left, left 1, up 1, left 1, up 1, left 1, up 1. So that's what I want you to remember about the parent function. It goes to the right and up in a 1-to-1 ratio. Over 1, up 1, over 1, up 1, over 1, up 1. The same as to the left. Left 1, up 1, left 1, up 1, left 1, up 1. When you begin multiplying the absolute value by a number, that's going to change that ratio at which it rises and runs. And we'll explore that by looking at a table of values. So for all three of these, I'd like you to put the same, actually for the first one, let's use the following values of x. Negative 2, negative 1, 0, 1, and 2. So let's plug those values of x into the absolute value and then multiply by 2. So when we put negative 2 in, absolute value is 2. 2 times 2 is 4. Put negative 1 in. Take its absolute value and multiply by 2. Put 0 in. Absolute value of 0 is 0. Times 2 is 0. When you put in 1, you get 2. And when you put in 2, you get 4. So these are the points we can plot. Negative 2 comma 4. Negative 1 comma 2. 0, 0. 1 comma 2. And 2 comma 4. And as you can see, the red graph is going to be steeper and skinnier because of that dilation factor 2. It makes the rise 2 while the run is 1. So multiplying by 2, again, makes it taller and skinnier. Next, let's see what happens when we put in a divisor, a number that's in the bottom here, when we divide by 3. I'm still going to start my table of values, actually put in the middle. I'm going to put in 0. But as I grow my x's, I'm going to use 3 and 6 this time instead of 1 and 2. And the reason for that is I want to get nice y values, and we're going to be dividing by 3. So 0 divided by 3 is 0. Absolute value is 0. You'll see what happens now when I put in 3. Divide by 3, you get 1. Absolute value is 1. When you put in 6, 6 divided by 3 is 2. The absolute value of 2 is 2. Had I used 1 and 2 instead of 3 and 6, I would have gotten decimal values here for y, and that would not be ideal. Next, let's use negative 3 and negative 6 going in the other direction, just to get an idea of what this graph is going to look like. When you put in negative 3 and divide by 3, you get negative 1. The absolute value is 1. And you put in negative 6, divide by 3, you get negative 2. Absolute value is 2. What you're going to notice in a lot of these is that you have some symmetry going on with your y column. See how it goes 0, 1, 2, and then 0, 1, 2 in the other direction. That's going to produce that V shape. So we have negative 6, comma 2, negative 3, comma 1, 0, 0, 3, comma 1, and 6, comma 2. And you can see here that this V is much wider and flatter than the parent function, which would have been rising at a 1-to-1 ratio. So while this is the parent function, the transformed or the dilated function when you divide by 3 gets flatter and wider. I'd like you to plot C on your own. I'd like you to use your own table of values and bring it into class and show it to me, and we'll have a little discussion about how it looks. On the next page, these are the fill-in-the-blanks for the bottom of your notes for section 4.6. If you'd like to pause it, read it, fill in the blanks, and think about it, any questions I can answer in class. Thank you.